Well, now we know how to find the solutions if we're given an x-intercept, right? If we have an x-intercept or a root solution or 0, then I can synthetically divide, knock it down to a squared, and then solve from there. But how do we know this number, right? So there's a theorem that's called the rational root theorem, or we could change that with 0 as well. So the theorem says, if f of x is a polynomial with integer coefficients, so this only works when all of our coefficients are integers, okay? Then every rational root, so it's important to remember what rational means. So to remind you, rational means something that can be written as a fraction. Right, so that would be numbers like 3, because 3 can be written as 3 over 1. I could do 2/3, because that is a fraction. I could do 0.666 repeating, because that turns into 2/3. I could do 2.5, because that would be 5/2. I could have negative numbers in there as well that can be turned into fractions. So like -7/2 would be fine, which is the same as -3.5. Okay. You can't have numbers like pi. Pi is irrational. So anything that has a decimal that goes on for forever and isn't repeating doesn't work. Or your square roots, like the square root of 2, that has a decimal that goes on forever that's not repeating. So that's irrational. So these are every rational root of the polynomial equation can be written in the form of p over q, where p is the factors of the constant term and q is the factors of the leading coefficient. It should be factors with an s, technically. Okay. So our p is the factors of the constant, the q is the factors of the leading coefficient. So remember, the constant is the thing on the end with no variable. The leading coefficient is the one with the degree. Okay. So if we find this piece of information, we have a list of all possible rational roots for that polynomial. So if we look at this example, we have this is p, this is q. Right? So our possible rational roots would be all of the factors of p over the factors of q. So if we think of the factors of p is 35, so 1 and 35. And 2 doesn't go into it, 3 doesn't go into it, 4 doesn't go into it, 5 goes into it 7 times, 6 doesn't go into it, and then that's all of my options. And then for q is 1. The only thing that the factors of 1 is 1, right? Now, it's also plus or minus. Notice when I looked at this, I didn't care if it was positive or negative. That's because I can get to this number using positive divided by positive or negative divided by negative. So what we have here is each one of these have a positive negative sign with it. So plus or minus, plus or minus, plus or minus. So then what I'm going to do is I'm going to divide each one of these by our bottom number. So I'm going to do this. So 1 divided by 1 is just 1. And then I'm going to do 5 divided by 1 is 5. And then we can do 7 divided by 1 is 7. And then we can do 35 divided by 1 is 35. Now, each one of these can still be plus or minus. So rather than write plus or minus on each one of them, I'm going to put them in parentheses and put my plus minus on the outside. It's a slightly lazy way of writing plus or minus on each one. Okay? So these are my possible rational roots. So then what happens is now I can figure out what my answers or what my rational roots are by synthetically dividing. So I could synthetically divide by 1 and see if I get a 0, or synthetically divide by -1 and see if I get a 0, synthetically divide by 5, see if I get a 0, and then if I get a 0, that would tell me that that's a factor or a root solution or 0, right? We're not doing that part today, so hold on that part. So this is the list of all of my possible rational zeros. So I just went from an infinite amount down to 8, because each one of these has 2. So infinite to 8 is really good. Okay? If we look at this next one, we're going to look at the factors of p over q. Again, our p is the constant, the q is the leading coefficient. So our factors of 6 are 1 and 6, 2 and 3, and then nothing else goes into it. So then on the bottom, I'm going to put plus or minus on each one of these. For Q, it's 2 this time, so we have both 1 and 2. So what happens is I'm going to take each top number and divide it by 1. So if I divide each one of those by 1, we get 1, 2, 3, and 6. Okay. Then I'm going to take each top number and divide it by the other bottom number. So 6 over 2, 3 over 2, 2 over 2, and 1 over 2. So then that gives me 1 half. 2 halves, which is 1, which I already have, so I don't need to rewrite that. 3 halves, which I don't have, and then 6 halves, which is 3, which I already have here. So I only get 2 more additional ones from the dividing by 2, which is the orange part. Again, each one of these is really plus or minus. So plus or minus 1, 2, 3, 6, 1 half, and 3 halves. So I went from, again, an infinite amount of possibilities to 1, 2, 3, 4, 5, 6, so 12 different options. So not as nice as 8, but much better than infinite. Okay. So let's take a look at this one. This is our P, this is our Q. Remember, it's always the constant over the leading coefficient. So we do 1 and 8, 2 and 4. Those are all of our ones for 8. And then 6 is 1, 2, 3, and 6. So we're going to get a few more on this one because we have more bottom numbers. So I'm going to divide each one of those by 1. So I get 1, 2, 4, and 8. Then I'm going to divide each one of those numbers by 2. So I get, I forgot to do orange. I get 1 half, 2 halves, which is 1, which I already have, 4 halves, which is 2, which I already have, and 8 halves, which is 4, which I already have. So we really just have this one from here. Okay. Then I'm going to do my third number, so 1/3, 2/3, 4/3, 8/3. So 1/3, 2/3, 4/3, 8/3. Oh, sorry, I saw 8, 6 in my mind because I was headed to the next one. Just kidding. So those are all the ones from our green ones. And then I can do everything divided by the 6. So 1, 6, 2, 6, 4, 6, 8, 6. So 1/6 we don't have. 2, 6 reduces to 1/3, which I already have. 4, 6 reduces to 2/3, which I already have. And 8, 6 reduces to 4/3, which I already have. So then I only get, oh, sorry, not 1 half, 1/6. 1/6. Okay. So then I get, I missed my gray color. And then this is all plus or minus. So this one is a much longer list than our other ones, but it still is knocking it down from infinity, so it's still nice. Okay. So that is our rational root theorem.